Good afternoon, everyone. Welcome to the 50 webinar of Vietnam Bioelectronic Community. The topic today will be the advancements in a control system, and we have two presenters today. The first one, Professor Ravi Rakesh Reddy. So please correct me if I pronounce your name wrong. So Professor, yeah, thank you. So Professor Ravi received his Bachelor of Technology degree from the Electrical Engineering Department of National Institute of Technology, Calicut in 2015. He received Master of Science and doctoral degree from the Department of Electronic System Engineering in Indian Institute of Science, Bangalore in 2020. He also have a postdoctoral experience in 2 years at the University of Houston, Texas, USA. Currently, he's working as an assistant professor at Department of Energy, Science and Engineering, Indian Institute of Technology, Bombay. His research interests include high performance control and safe commissioning of motorized for electric vehicles and a power converter for electric vehicle charging. So he will present the topic high performance control of induction motor drive for electric vehicle application. Professor Ravi, can you go ahead and say something and start your presentation? Thank you.
Yeah, thank you, ma'am, for the introduction. So, my name is Ravi Prakash Reddy, and I'm currently working as an assistant professor at the Indian Institute of Technology, Bombay. So, today I would be presenting on this topic, high performance control of induction motor drives for electric vehicle applications. So, here is the introduction of the presentation. So if we look at the image or the graph present on the right side over here, which shows the global carbon dioxide emissions each year, we see that these emissions are increasing at an exponential rate almost. And among these emissions, the transportation sector in particular accounts for about 25% of global carbon dioxide emissions. So therefore, to bring down these greenhouse gas emissions to a very lower extent, one of the areas that we can work on is in faster adoption of electric vehicles, right? And we have also seen that most of the governments from various countries are also promoting the electric vehicles in a great way. And these fast growing of the area of electric vehicles also has significant challenges in terms of the advancements in the existing charging infrastructure and also in the high performance control schemes that we apply for EV applications. So I had worked during my PhD on the usage of induction machines for EVs applications. Of course, permanent magnet machines are very widely used these days for EV applications, but the problem with permanent magnet machines for its use in EVs is its high cost, right? Even though the permanent magnet machines have very good power densities, which are really required for EV applications, but the cost of the permanent magnets can make the overall EV much costlier. And in addition to that, there are also a lot of issues with the aging of permanent magnet over times, and therefore we thought we would look at on how we can improve the induction machines for an electric vehicle application point of view. So now again looking at as to why these high performance control schemes become very important for electric vehicle applications, we can have a look at the study published by MIT on the temperature levels of various components present in an electric vehicle. And we see that among all the various parts and components in an electric vehicle listed here, electric machine is the one that is subjected to a lot of temperature levels, right? In an electric vehicle, the motor can have temperatures as high as 110 or 120 degrees Celsius. So if this happens, the parameters of the machine especially the resistive parameters of the machine, are prone to change very easily with temperature. So therefore, if the parameters of the machine change, that is going to result in the degradation in the performance of both steady state and transient characteristics of the speed control method that we employ for electric vehicles. And conventionally, people have been using vector control techniques, also called field-oriented control techniques for electric vehicles. But as we know from the literature, that these vector control techniques are sensitive to the variation in machine parameters. Right? For instance, if you talk about indirect rotor field-oriented control scheme, we may have to estimate slip from the machine model, and this estimated value for slip is going to depend upon the parameters like the rotor resistance and the rotor inductance. So therefore, if temperature changes and if these parameters vary, then it is again going to result in the deterioration of the performance of this vector control method. And these issues have definitely been taken care in the literature for induction machines by making use of a lot of parameter adaptation algorithms. But the problem with the use of parameter adaptation algorithms is that it is again going to demand for the additional transducers, and therefore the overall cost and the reliability and the complexity of the system is going to increase. So therefore, in order to address these issues, we came up with a new control method. Before even going on to this new control method, firstly, if you look at the various control schemes reported for induction machine drives in the literature, we could broadly classify all those control algorithms and put them into two major varieties. The first thing is the scalar control of induction machine. In scalar control of the induction machine, as the name itself says, we do a scalar control, meaning we control only the amplitude and frequency of the stator voltage that is being impressed on the stator terminals of induction machine. And the phase part of it, the phase angle control of induction voltage, is not really there, is not really employed in the case of induction machine, resulting in its sluggish response. But however, the advantage of scalar control method is that these control techniques are really robust against the variation machine parameters. Even if the parameters do vary, we do not have the problems like the dependency of the slip on the rotor parameters or the changing of slip due to the operating conditions as the parameters vary, right? But on the other hand, we do have vector control techniques, and vector control techniques differ from scalar control techniques in terms of the improved torque dynamic response, right? The torque response of the vector control based induction motor drives are really superior when compared to its scalar control counterparts. Mainly the reason being the inclusion of the phase angle control as well in the vector control techniques. So therefore, since all the three quantities, namely the amplitude, frequency and phase of stator voltage are controlled in the case of an induction machine while using vector control techniques, it results in superior torque transient response characteristics, which is what is lacking in scalar control techniques. Because in scalar control techniques, we do not really have phase angle control, and therefore the dynamics are going to be pretty slow. But the issue with vector control techniques is that these control techniques are sensitive to the variation in machine parameters, as we have just discussed in the previous slide, right? So that way, if we look at the broad classification of these two control techniques, both have their relative advantages and disadvantages. And from an electric vehicle point of view, it would be better if you have such a control scheme that has both performance characteristics as well as robustness features. So therefore, in the proposed control method, we have tried to ensure the robustness features of scalar control while having the high performance aspects of vector control techniques. In a way, we try to combine the advantages of both the vector control and scalar control techniques, which results in a hybrid control technique. And this is done using the concept called transient vector estimator in the proposed control method. And as I said, in scalar control technique, the robustness features of it is really an attractive feature for us, because we really need the control structure to be robust against the variation machine parameters. As in an electric vehicle, definitely the machine is subject to the variation machine parameters due to the change in operating conditions. Therefore, if we could impart phase angle control part of it to this way of control, or to the steady state scalar control of induction machine, we can have enhanced transient response as well. So in order to understand on how this phase angle control really plays a role in improving or enhancing the dynamic response of torque for induction motor drive, we had initially carried out some analysis. And for the analysis, we have considered the equivalent circuit that is shown over here. So this is the normal steady state equivalent circuit of induction machine. And to the equivalent circuit, if we apply the KVL and KCL equations, we would land up with the following equations. The first two are the KVL equations on the stator and rotor sides respectively. And third equation is the expression for the rotor flux linkage in an induction machine. And the final equation is the equation corresponding to the magnetizing and the core loss branch. So, and when we speak of these high performance control circuits, we keep the amplitude of flux in the machine constant, right? Only then I can decouple flux from the torque, and therefore torque will have enhanced torque dynamic, enhanced performance, enhanced dynamics. And if we keep flux in the machine, amplitude of flux in the machine constant, we can say that the torque is directly related to the rotor current, right? And therefore, if one is interested in enhancing the torque dynamic response, we will have to control the amplitude of rotor current also instantaneously. Only then we can have enhanced torque dynamics. So therefore, let us assume for some time t less than t1, the expression for rotor current be given like this: IR of t is capital IR sin omega is t. And since we are interested in enhancing the torque dynamic response, let us instantaneously change the rotor current at time instant t1. Therefore, for time t greater than t1, the expression for rotor current becomes this, right? And if we substitute for this expression for rotor current in the previously obtained KVL and KCL equations, we can see that the expression for the rotor flux linkage and the stator voltage are obtained as given below. Now, let us try to formulate in this slide all the conditions that one would have to fulfill in order to have faster torque control in the machine. So, initially, we can see from the expression for the rotor flux linkage over here. And as I said in the previous slide, that it is important to keep the amplitude of rotor flux in the machine constant. Only then we have enhanced torque dynamics. We see that the ratio of the rotor current to the slip has to be changed in this fashion, where IR dash and IR represent the amplitude of rotor current before and after the transient. So therefore, this equation basically indicates that the amplitude of rotor current has to be changed in accordance to the slip ratio. So therefore, this becomes the frequency control of the stator voltage of induction machine. Now, if we also look at the expression for the stator voltage before and after the transient, and if we work out on the amplitude part of it, we would see that we may have to change the amplitude of stator voltage as governed by this relation, which is again very clear from the amplitude of the stator voltage equation. So therefore, this can be regarded as the amplitude control of stator voltage in an induction machine. And finally, looking at the phase part, we can arrive at the following relationship in which one has to control the phase of the stator voltage of an induction machine if it has to result in the faster torque dynamics. So therefore, from this slide, we can conclude that if one has to improve the torque dynamic response, or if one has to instantaneously control torque in an induction machine, we must control amplitude, frequency, as well as phase. Right? Only then we would have faster dynamics in the system. Now, to validate the analysis that we have projected in the previous slides, we had initially conducted some simulation results using MATLAB Simulink. And from the simulation results, we can infer that in the case where there is no phase angle control employed, and when a step change in the load is given, we see that torque exhibits some dynamics in the system. This is as a result of dynamics clearly seen from the rotor flux linkage and the rotor current. However, when we employ the phase angle control as well, which is what one should input if it has to result in enhanced torque dynamics in the system, we see that torque almost changes instantaneously without any evidence of transient. So therefore, from this simulation result as well, we can conclude that if we have to control the torque in an induction machine instantaneously, we must input phase angle control as well. Now, therefore, after having realized that it becomes very important to input the phase angle control as well to the steady state scalar control portion, in order to have a resulting control which has both robustness aspects as well as high performance aspect, we have taken the scalar control to be the steady state platform. And to this scalar control, we have added the transient vector estimator part, which acts as a third control input to the already available amplitude and frequency control of stator voltage, and therefore the resulting control is going to be having high dynamic performance. And since anyways we have scalar control in the steady state portion, the robustness features of it is already going to be ensured, right? And this is the phasor diagram for that, where we have the estimation for transient vector estimator VST given in green color over here to be added to the steady state voltage vector VS, so that the resulting voltage space vector VS dash is going to have enhanced torque dynamics in the motor drive application. So this is the block diagram of the proposed speed control method. In the proposed speed control method, we have V by F control or the scalar control in the steady state portion. We have a speed reference being compared with speed feedback. The speed controller is going to give you slip, and we also have a feedback compensation of the omega feedback. When both are added, we have the synchronous speed. The V by F profile of it is going to give you the control voltage. Once you have the control voltage and phase of it, you could actually transform them to alpha, beta, or ABC, and then compare with the appropriate triangle carriers. And once those PWM signals are given to the induction machine, the machine would spin at your set reference speed. And to the existing VYF control portion, if you see, we have made one change to that in terms of the ability to incorporate the VSDT and VSQT, which are the voltage vectors that are being estimated from the transient vector estimator block that is shown over here. By basically adding this VSDT and VSQT, since control is done all in the DQ domain, the synchronously rotating reference frame, we have provided a provision in the steady state VYF portion so that we could input VSDT and VSQT over here, right? So now this transient vector estimator block is basically again based on the indirect rotor flux state model of induction machine, wherein we have the D-axis current reference being compared with the actual D-axis current, and the error is passed on to a PA controller to output this VSDT. Similarly, we also have the Q-axis current reference being compared with the feedback value or the sensed value of ISQ, and the error is again compared to the Q-axis current controller to output the Q-axis component of the transient voltage vector. Now, once we add these two, we have VSD and VSQ coming from the steady state VBF portion. Now, since we can control the phase of it also over every PWM cycle over here, we are also inputting the third control input to the proposed control method, and therefore we have the enhanced torque dynamics in the system. However, and similarly, since the steady state portion is based on the VYF control, there is no need for the estimation for slip, right? For example, if you look at the steady state portion, slip is something that I can readily take from my VYF control portion. So therefore, I do not have to worry about its dependency on the rotor parameters like the rotor inductance and the rotor resistance, which is what would happen in typical vector control or indirect field oriented control schemes. So once we had done the validation, the simulation validation and analytical validation, we have also conducted experiments, and the photograph of the experimental setup is shown over here. So we have the main grid, the three-phase grid, which is then passed on to a three-phase auto transformer array varia, and the output of this three-phase transformer is connected to a DC link, and the DC link is connected to the three-phase two-level voltage source inverter, which is shown over here with the gate drives present on the top, and we have used semicron IGBT switches over here. Now the midpoints of the three half bridges and the three legs of this three-phase two-level inverter are connected to the three-phase terminals of the star-connected induction machine. For the purpose of loading, we also have a DC generator over here, wherein we have the provision to load it. And all the control algorithm is implemented inside a DSP. This is a TMS-based TMS320F28335 digital signal processor. And current sensing is done using LEM Hall effect current sensors. And we had carried out these results on a three-phase 4.7 kilowatt induction machine rated at 400 ohm. Now, these are some of the experimental results. We have validated for the performance of the proposed control method in terms of both the robustness and the high performance aspects. Initially, presenting the transient response characteristics, we see that when the speed reference is changed from 0 Hz to 40 Hz in steps of 10 Hz, we see that the feedback speed and sensed speed is closely tracking with the reference speed in the steady state. And during the transient, at any given point of time, we see that the D-axis component of current, which now represents the flux levels in the machine, is kept at its constant value. And therefore, we have the complete decoupling between the D-axis and Q-axis current control and D-axis component of current, meaning that there is decoupling between torque and flux, because we see that during the transient portion, only the Q-axis component or the torque producing component is going to change. Similarly, we had also carried out the experiment by loading the machine from no load to 50% load, and we see that during this during this loading condition, again only the Q-axis component of current, which is responsible for the torque changes in the machine, only responds to the changes in the load torque, and therefore we see that D-axis component of current is constant, while Q-axis component varies. Therefore, the phase current also jumps to its U higher value to meet the increased load demand. So that way we have the decoupled control between the torque and flux in the machine being retained in the proposed speed control method as it representing the vector control technique. And the proposed speed control method is again compared with both the V by F and the existing scalar control and the vector control methods. And we see that when it is compared with the V by F control method for the speed reversal of the machine from negative rated speed to the positive rated speed, both D and Q axis components of the currents do change. As a result of this is because of the non-presence of the decoupling between the torque and flux in scalar controlled induction motor drives. And we also see that the phase current reaches to very high values in the case of scalar control method. And in proposed control method, similar to vector control method, since we have the current limits, and during the acceleration period, we see that only the Q-axis component of current changes, and therefore current stays in a common band, and therefore we make sure that the current is not shooting up to very high values. So that way, when to conclude for the comparison between the scalar control and proposed speed control method in terms of the dynamic response, we see that the proposed control takes an upper edge over the scalar control method in terms of the enhanced torque dynamic response. And we can also work with reduced ratings of the inverter with the proposed speed control method. And when we compare the vector control method with the proposed speed control method, here we have to compare it with parameter sensitivity. And we see that when the rotor time constant in the machine is changed intentionally to a 20% higher value, we see that both D and Q axis components of the currents do change in vector control method, indicating its losing of the field orientation. And however, in the proposed speed control method, since slip is tapped from the steady state V portion, since it doesn't depend upon the values of the rotor time constant, we see that these remain unaffected. So once we had verified the proposed speed control method and a laboratory prototype, we have also tested it on an open source electric vehicle platform called Tabby. And this is the open source electric vehicle platform where we use a 25 kilowatt 210 amp 150 hertz induction machine over here. And on this Tabby, on the open source electric vehicle that we purchased, except the chassis and the induction motor part of it, everything else is replaced with the ones that we have designed in the lab. So I have designed the pre-charging circuit for the DC link capacitor, because when the battery is directly connected, interface to the motor using a DC link, there is a huge chance of surge currents flowing through that, because the capacitor is initially uncharged, and therefore we may have some sort of pre-charging circuit for the DC link capacitor, wherein we would use a very high value of resistor at the starting in series with the battery, so that as the time passes, when the capacitor reaches to a safe voltage, the contacts of the terminals of the contactor would automatically be closed, and therefore we would not have any issue of the surge currents being flown into the capacitor at the time of starting. And all the control algorithms, the interfacing of accelerator and brake units were taken care in the design. So this shows the validation of the proposed speed control in various stages. We have initially developed a water-cooled inverter, because we are dealing with very high power levels. We have to take out a lot of heat from the semiconductor switches. We have a water-cooled arrangement from that. And then we validated the proposed speed control method initially in an electric vehicle by lifting the wheels up. And finally, we also had tested the performance of the control method by running it on the road. So another interesting feature in the motor drives for EV applications is the self-commissioning of induction motor drives, which basically caters or allows to the auto-tuning of the controller parameters when the machine is not yet started. Right? Again, if you look at the parameter sensitivities, the parameter estimation schemes present in the literature, we could see that there are only 4 parameters out of the 5 that can be individually estimated. Right? And often, even during no-load and block rotor tests, we make an assumption on the values of stator and rotor leakage inductances. We assume them to be same, and in fact, they cannot be separated. This is due to the fact that the order of the system is only 2, and therefore we have only 4 parameters that can be individually identified. But however, there are 5 parameters that need to be estimated, like the stator resistance, the rotor resistance, stator and rotor leakage inductances, and the magnetizing inductance. Therefore, it makes it practically difficult to estimate all of these 5 parameters, and therefore we can get only 4 out of these 5 parameters, and often people assume a relation between stator and rotor leakage inductances. In most cases, we assume them to be equal, and that is how we could get the parameters. But if we make such an assumption, again, the accuracy with which we estimate those parameters is not going to be guaranteed, right? And therefore, if the parameters are not being accurately estimated, we may have to again compromise on the performance of the high performance control schemes that we employ for any motor drive operation. So to overcome this issue, what we have done is we have also considered the iron loss resistance in parallel to the magnetizing inductance, in which case the order of the system becomes 3, and therefore we have 3 coefficients in the numerator and denominator, and we have 6 coefficients with 6 parameters equivalent over here. Therefore, all the 6 parameters could be individually identified. But however, there is a challenge here in terms of the dependency of the iron loss resistance on the fundamental frequency of operation. This issue was taken care in the proposed method by basically exciting the machine with 2 different voltages of different amplitude and frequency and keeping the ratio constant. So that way we were able to estimate all the 6 parameters of the induction machine individually without having to make any of the assumption on any of the parameters being estimated. So yeah, that's all I have to present about. If you have any questions, I'll be happy to answer.
Yeah, thank you, Professor Ravi, for really nice presentation.
Yeah.
So yeah, so from the audience, if you have any question, you can unmute and directly speak to the presenter, or you can type in the chat and I can speak that for you. Hello.
Hello. I have a question. I'm there from EVS Lab.
Yes.
Yep. I have a question about the hardware. And can you
Yes.
Yep. Can you back to the picture with your hardware? Yep. This.
Yes.
Yep. This one. Yep. So as I see that you use the 3-phase with 4000 volt and nearly 5 kilowatt. So what MOSFET you're using?
I'm using an IGBT. It's from Semicron. Yeah, it's an SKM. I forgot the exact part number of the IGBT, but it is from. It's a half bridge module. Yeah, where you have both the top and bottom devices integrated into one module, the half bridge module. Yeah, and so yes, that is the IGBT that I'm using, not MOSFET.
Yep. So as I see that the trend will be SiC MOSFET. So what do you think about transfer from IGBT to MOSFET?
Yeah.
So the SiC MOSFET.
Correct. So in the work that I have worked in the proposed work, we have really tried to concentrate on the control algorithm, not from the device perspective. So since the work is on the control algorithm, even if I replace from an IGBT to the silicon carbide, the dynamics or the performance validation of it is not going to be affected. But you could have advantage in terms of, for example, if I use a silicon carbide device, and since I'm able to switch at much higher switching frequencies, maybe I would have much smoother currents in the machine, right? Because if I can switch it at higher frequency, but again, you have to look at the switching loss over there, right? So there is always this trade-off between the size and the efficiency of it. But if you ask for the control point of view, the work that I propose can easily be translated to dealing with silicon carbide devices as
well. Yep. Thank you so much. And as I see that in your experiment result, can you I have a question about the yep. I see that John, your experiment result is very good, very good. It's flat, almost flat. So can you compare the your result with the another public? So I mean with other public solve they can be solve the same problem with you. And what is happened with what is your their result? I mean the comparison.
Okay, the comparison part of this one.
Yep, I want comparison about performance with you with your research and the other.
Yes.
Yep.
Yes. Yeah. So that is where we try to compare the proposed control method with the methods already existing in the literature. And as I mentioned, when we compare for the dynamic response of it, we see that with the existing scalar control method, both ISD and IS2 change. Right? It means it sort of indicates a coupling present between the flux and torque producing components, right? Between flux and torque. But in the proposed control method, we see that the flux producing component is almost constant, while only the Q-axis component of it is changed. So that way it would have the enhanced torque dynamics system. Same with the existing vector control method as
well. Oh, I see that. Thank you so much. It's very I see it's very good, very good result. And thank you so much for answering for me.
Thank you.
Yeah. Thank you so much.
So we are welcome for more questions. So Professor Ravi, you said that you use IGBT, right?
Yes, correct.
So how about the switching frequency in this experiment?
So I have used 20 kilohertz.
Okay, 20 kilohertz. Oh, yeah.
Yeah.
And I see you also have deployed the system into a car, right? In some
sorry, the load system?
Yeah, this system in the car. Like
the load.
You have already have the experiment in a real electrical car, like you show in
Correct.
Okay, yeah, really nice experiment.
Yes.
Yeah. Okay. Yeah. And you have it in your lab right now?
Which one?
This system.
Yeah, this system, yes. So this was from my PhD at the Indian Institute of Science. We still have it. Some of the students are still working on it.
Oh, nice.
Yes.
Yeah. So if yeah, I don't have more questions to ask.
Thank you.
This is not really my my field.
Okay.
So
Okay.
yeah, let me see if we have more questions from the audience or other professor want to communicate a little bit. Otherwise, we will hello Dave. Are we moving to the rec and the slide of the sponsorship?
Yes. Before we move to the second presenter, I have one more question.
Okay. Welcome.
Yep. Can I ask? Can I ask about the control the MCU? I want to ask about the MCU and
okay.
Do you are you using the TI chip? So
yes.
Yep. And and what do you think about and I want to ask about why do you use the TM and this chip instead of another? Because as I know, we can use we are using the ST microchip in our labs to control the MOSFET and to the control. So why use the TI?
Yeah, I mean, yes, there are actually a lot of DSPs, right? There are from different manufacturers have the different versions of that. Now we have been traditionally, our lab has been using all these Texas Instrument based chips, because there are a lot of modules specifically for power electronic applications. Like it has got EPWM module, it has an ADC module, it has a DAC module, right? And since I'm working with just a 2-level inverter, I just need maybe 6 PWM, right? And I would need 3 ADC, right? I'm just sensing 3 currents, so I need 3 ADC. And I would need maybe 4 or 5 DACs to do the waveforms if I'm talking about a 4-channel oscilloscope. And this is one module where I found that all these, this is one DSP where I found that all these modules are brought out easily, and it's so convenient to use. So that is why we have sticked on to this particular Texas Instruments based DSP. But again, there are a lot of things available in the market. It should not really affect your analysis or your control implementation. We are free to use any other chip as well.
Yep. And thank you so much. And another question is, as I see that you are using the 400 phone bus. So
yes,
as I see in our in my research, I'm researching about the 800 phone bus, the 800 phone bus system. So do you think about when do you use the 400 bus and change to the 800 bus system? So what is challenge? And your proposal can be used to change from 400 bus to the 800 bus.
okay. So here the 400 volt that I said is actually not the DC bus voltage, but is in fact the machine rated voltage, right? Because in India we have a 230 volt single phase system, and the standard of the 3-phase system is 415 volt, right? Line to line RMS value is 400 volt or 450 volt in India. So most of the induction machines that we can buy off the shelf are rated for this voltage. And of course, if the machine is rated for 400 volt, the DC link voltage of it has to be kept much higher, right? From the sine PWM, we can work out on the minimum value of DC link voltage that one would require if you have to drive a 400 volt induction machine, right? That again depends on sine PWM or space vector PWM techniques that you can use. But in the EVs, yes, as you said, on the DC link, on the battery and the DC link point of view, there are standards over here from 400 volt to 800 volt. So typically today, most of the 4-wheelers are using a 400 volt battery system. And one of the main challenges, or one of the main reasons that we see a recent shift from 400 volt to 800 volt system is again on the current levels that we have to talk about, right? If you have a 400 volt battery, for the same power level, the current is going to be drawn more from the battery. But if I have an 800 volt system, for the same power level, the current is going to come down. So since with an 800 volt, I can work with reduced current levels for the same power level, the size of the cable is going to come down. So the thickness of the cable is going to come down, which makes sense for an AV application, because otherwise you may have to deal with a lot of thick cables. They add to a lot of weight of the system, and your battery range also is going to come down eventually, as I put lot thicker and cables in the system. But the challenge with 800 volt system is again the safety perspective, I would say, right? If you have to have more kWh rating. So safety is one thing. With 800 volt, we are not going, I mean, at least it's not safe as that of a 400 volt system.
Yeah.
So, yeah.
Yeah, thank you so much. And it's very helped me to understand more about the system, the voltage system bus. And thank you so much. I don't have a question further. Yeah, thank you so much.
Thank you.
Yeah. Dr. Bang, can you hear me?
Yeah.